Jambo, Mbote, Hotep, Nangaref, dalal jàmm ci Yesu Krista sama musalkat. So, Akwaba to you. I am Marcelin Nidabo. I am a PhD on control systems. I am a consultant engineer in industry and an independent researcher. So, just to inform you that I have been talking about dynamical systems in this series of videos, and then you will be able to see previous videos through which I have presented so many concepts, many things, including interesting stuffs that I have introduced for the first time in control systems in the whole history of uh, this discipline. So I am an African from Senegal in West Africa. So I was talking about something particular that I have introduced in control systems is that there is only one time constant for a dynamical system of second order. Okay, so you can check my previous videos on my YouTube channel and you will see all the explanations related to that, related also to some new concepts that I have introduced, like for example, a relative time constant. Uh, time constant, uh, constant of the surface of time, for example. These are concepts that I have introduced, so you will be able to check on previous videos to see these scientific innovations that I have brought to the world of control systems. So today I will be talking to you about the computation or the calculation of the solutions of ordinary differential equation of second order without going through Laplace transforms. Okay, so please, if you are ready, let's go. But before doing that, just to remind you that I have talked about different subjects in previous videos for first order and second order dynamical systems. I used particularly uh, an exclusive temporal approach, meaning that I will be computing all the things only using time. I don't use transfer functions. It is not because I am against or opposed to, no, it is just because I wanted to explore a new vision, and this yields me to new paradigm and new methods that I have discovered in control systems. Okay. So thank you for your attention. So now for the next, let's go. So please note that here is my next book. The book will be appearing soon, very, very soon, probably next year in January. I hope so. And then this is a French version. I will be preparing the English version in the next months. Okay, in order to be able to share with you the stuffs. But anyway, you already have, I mean, some videos in English in order to take advantage or to take knowledge from them. Okay. So, thank you very much and be aware that all the videos that I have done are the concepts and the theories are synthesized in this book. Okay, so if you buy one, I will give you one bookmark. Okay, so now let's go. For this example that I consider, I took it in the book of Godefroy Onwubolu. The title is Mechatronics Principles and Applications. So at this page 419 or 419, there is a given example that is the following. If you consider this transfer function as the ratio between 3 over s plus 2 times s plus 3, okay, this is the transfer function that you could consider, that you should consider. And this, you can write it as separated fractions, okay, a sum of two fractions. It is the fundamental principle of algebra, that is partial fraction expansion, okay? And then going through these calculations, you will be able to to determine K1 and K2. And then once you compute them, you will be able to do the final calculation, from this formula. And then the final calculation that you will be able to do is to replace just the constants by their computed values, as you can see here, for example, for K2 and for K1, it is 3. And then written as this expression, you can make a factorization by 3 here, and then you have a sum of two transfer functions of first order. And then doing so, you just refer to a Laplace transform table here, where you can see that thanks to line 5, you will be able to write the temporal expression of the solution of this transfer function. Okay? So if you look at this process carefully, you will be able to see that there are risks of mistake, of course, because going from one line to another, you can make mistakes. So you should be very careful computing or doing this computation. In some contexts, it's not easy to derive these uh, expressions. Okay. So what in some contexts means that if you check the roots of the denominator of the transfer function here, it depends. They can be double. They can be also um, let's say complex numbers with an imaginary and a real part that are different from zero, both. And then by with that configuration, sometimes it is not very easy to do this kind of computation. Okay, so this is why I propose you another way to check the results that you want to check. Excuse me for my voice. So I'm sorry. So if you consider second order systems, a second order dynamical system, as I talked about this during some previous videos, and then you can have for them, if you check it, okay, in a given way, you can have them for, you can check two different responses, autonomous response and then also initial response. So, to compute the autonomous response, what we do, we consider that the initial condition of the variable is different from zero, while the one of the derivative of the variable is equal to zero. Okay. Going from this hypothesis, we have this expression that is given here, and that is equal to the solution of your differential equation when the damping ratio is less than 1, meaning that when your system is underdamped. I talked about this at the beginning, is that this is the only time constant, okay, of a second order system, whatever its damping ratio, okay. And this expression is equal to the double of the relative time constant. Please check the video titled One Single Time Constant for a Second Order System, and then you will hear and see all the demonstrations that I have made, going from the concepts of ordinary differential equation of order n up to order 2, and then where I have derived and introduced these concepts again for the first time in modern control engineering. Okay, so I was saying that the autonomous responses, meaning that when the input is equal to 0, is given here for S of t for different values of the damping ratio, as you can see it here, as you can see it here also and here. Okay? If you do the same for the initial responses, the expressions are given like this, where you have d over a0 is the static gain that you have here, and then the k0 is the amplitude of the step input. And then the expressions according to the damping ratio are given here. The solutions, expressions of solutions are given here, for example, and here, and here. Okay? So what does it mean? It means that if you are solving a differential equation, you just need to check to the damping ratio. And you don't need to go through a transfer function first, and then after you do the computations through the principle of fraction separation, partial fraction separation. It is not necessary. You can just compute the damping ratio. If it is less than 1, so you choose this solution, and then all the elements are available to be computed, because you will be able to compute the natural pulsation, the damping ratio also, and then all these elements normally they are given, okay, in the expression of your ODE. So let's go for first example. Let's recall, for example, our first expression, that is f of s equal to 3 over s plus 2 times s plus 3. So this is the expression of our transfer function, if you remember. Okay, it is here, right? We just take this and then we're gonna do the calculations. So from here, when you develop the expression under here at the denominator, what you will be having is s squared plus 5s plus 6. Okay, this will be the expression. If you go from here and write the transfer function, you will be see that the expression here, the s squared, you will have it here. Okay, and then the 2c omega n will be equal to 5, and then the omega n square will be equal to 6. And then, so the b will be equal to 3. Okay, so if you check it that way, you will see that if you want to compute the omega n here, you just take 6 here by identification, okay, by identification term by term, okay, you will be having 6 equals omega n squared, and therefore omega n is equal to the square root of 6 plus minus, but as we are interested only by omega n, so we have the plus minus square root of 6, we will just take the positive value, that is the square root of 6, and then the omega n is given here. Okay, now as it is given, we can compute the c from this expression, meaning that 2c omega n equals 5, and therefore c equals 5 divided by 2 times omega n, what you have here, and therefore we have a c that is equal to 1.0206, which is greater than 1. And as it is the case, we can directly consider here, we can directly take here the value that we need, okay? Meaning that the solution that we need, we directly consider it from here, right? And then, because this is the solution, the autonomous solution for systems with that are overdamped, okay, or with a damping ratio that is greater than. These are, of course, initial responses that we have here, the corresponding initial response. And then here, if you check this expression, we have the static gain of this system that is equal to 0.5, and then the tau s is equal to 1 over the c times the natural pulsation. So this is a time constant according to Double's definition, meaning my definition I have introduced, and then that is equal to tau s equals 0.4 s, right? So if you have this expression, of course, it will allow you, for example, to be able to compute in a simple manner the time responses of your system, even if it is overdamped, for example. Because you have this expression here, you will be able to use all the formulas that I have presented, Doubles formulas, meaning my formulas, on the previous expressions that you will be able to see in a previous video where I give different explanations about how to compute the time responses, whatever the damping ratio. Okay? And you can take it for specific damping ratios that are given greater than 1, less than 1, or equal to. Okay? So from here, how we proceed? If we want an autonomous response of this expression, or of its corresponding differential equations, meaning the second derivative of s according to time, plus 5, the first derivative of s according to time, plus 6, the expression of s according to time, it is equal to, let's say here is 3 multiplied by the entrance. And then if we are based only on this expression, we can directly derive this knowing after computing, after having computed the damping ratio. Okay, and then the expression here, if you consider the initial condition, you just consider a value that is different from 0 here. And then going from there, you compute here the c omega n, t minus td is the time you don't touch. You compute the square root of c square minus 1 multiplied by the hyperbolic sign of omega n. You know it, where it is omega n, it is here. So you replace omega n here. T minus td we don't touch. The square root of c square minus 1 we compute, and then we add finally the hyperbolic cotangent of this expression that should be also, that can be computed. And then you do the same thing for the second expression for an initial response. And you will have what you're looking for. For example, b over a0, it will correspond to 3 over 6 here, and 0.5, excuse me, that is a static gain. And if your k0 is equal to 1, you will have all this expression that is equal to 0.5, and then we keep doing the same computation as here, okay? Except that the SDP, you don't have it in this expression, okay? So recall that it is possible, once you know this, you just go and take the corresponding percentages according to a given alpha r, that is a coefficient that will be multiplying the time constant in the sense of double, meaning mean. And then from there, you derive your those, you derive everything that you need. Okay? So if you consider the next example, go from this one, right? We go from this. We do identification term by term here. And then we derive its corresponding omega n, that is the natural pulsation. We derive also the damping ratio, and then we are in the same case. We compute the static gain of our system, meaning that we take 12.5 divided by 25, it is 0.5, and then we compute the damping ratio of our second order system, that is equal to this expression, okay? And then we do the same philosophy. We derive the S of t for the autonomous system. For the initial response also, we have the solution. Okay. And by the way, this expression of damping ratio that is equal to 1.2, you can refer to a table in my book where you can just come and see how we compute, for example, the time response at 5% if you have an autonomous system, or at 95% if you have a step response. And then you will see how to apply the formula according to the natural pulsation. Okay, so the solutions, analytic solution can be given, but also the temporal performances can be directly computed from this expression of C. If you have a C that is not put in the table I am talking about, so please check other videos, and then share the videos also to different people such that they can see that there are new things that can be very helpful for them that I have discovered. Okay. So if we go further, you can see that we consider this example, and then by the same process here, before doing identification, of course, we divide by this 2, that is a constant coefficient here. and then the omega n is equal to 9. Okay, we derive it. The damping ratio here is equal to 0.875. If you have this damping ratio, what you have is an underdamped system, and the solutions for an autonomous system or for an initial response are given here. And then you check the same process to compute them as I described previously. So here the static gain is 1.5 because we consider 243 divided by 162. Okay, it gives you this expression. And the time constant of our second order is given here, which is equal to 127 milliseconds. So remember that with this value of damping ratio, if it appears in the table, you will be able to find directly the time response at 95%, at 90%, at 80%, at any percentage that you need to compute, you will be able to compute the time response before even doing computation. You can compute directly the time of the first peak of the overshoot because here the damping ratio is less than 1. You can compute directly. I have the formulas for this, the time response for the instant at which the output is crossing the equilibrium point. Okay. And then also you can compute the settling time value also according to formulas that are known. Okay. So it is very important to underline that all these formulas I am talking about are not approximations like in modern control engineering today. These are formulas that I have introduced and explained, so I invite you to check again corresponding videos in the given examples that I have shared on my YouTube channel. Okay, so going from here, if the damping ratio is computed and equal to 1, you take another formula that is here, and then with this formula you compute everything, and then in through the same process, and you have also the time constant that is given here. So directly, what is the advantage of this? Is that you don't have to use, for example, um, you don't have to use Laplace transform tables with the risk of making mistakes. You don't have to use also all the partial fraction method approach. Okay. And then once you get the response, you can directly compute the time responses because I have all the formulas. So you see that I don't, or we don't need Laplace transforms to go from the differential equations here to the solutions that we are looking for. Okay, these are expressions of the autonomous response. Z and this one for the output response. Okay, so please don't forget the time constant. Okay, this is a static gain here that is computed. To compute the static gain, you just put at 0 the derivative and the second derivative here, because if you reach the steady state, variations are so small and then they are assimilated to 0, so you just stay with this expression. This is why we talk about static gain, as I explained in other videos. And then here you have the static gain that is equal to 1. Compute always the time constant of our system, celebrating the result I have brought in control systems. And I think that this is something important, not just because it is me, but it is because also it's really, in fact, important. It is based to these values that I have, to this process and paradigm that I have computed all the formulas for time response and also for temporal performance of our system. Very important. So, okay, thank you for watching. If you have any question, please feel free to reach out, and then I will be very happy to answer to you about these explanations I given today, meaning that I don't need or we don't need systematically to use Laplace transforms in order to find solutions of an ordinary differential equation of second order. This is a book to appear, as I presented at the beginning of this video. It is coming very soon, probably in January 2025. So I hope that you are preparing yourself to buy this book. This is the French version. English version is under preparation for the next month. So again, thank you for watching, and then I hope you will be able to share this video with your beloved people, your students, and then also to like and subscribe to my channel to support what I'm doing. So anyway, I want to thank you again very much for your attention, and then I hope we will be able to talk very soon. So enjoy your day, stay blessed, and then I say to you, Diagyophete Theoturbias.